Alright, morning everyone. We'll be starting class in 1 to 2 minutes time. Alright, morning everyone. So today's lectures are going to be based on the topics of sampling and the discrete time Fourier transform, which we're going to be referring to as the DTFT. And in the first lecture, which is sampling, we're going to discuss the importance of sampling as to how we produce discrete time signals, as well as how we can transform these discrete time signals into their discrete frequency counterparts. And then how it is that we use that discrete frequency counterpart to formulate the discrete time Fourier transform in our second lecture in particular. So let's get started in the first lecture. So we observed in last week's lecture that the continuous time Fourier transform allowed us to take a continuous time signal here and obtain the continuous frequency representation of itself, known as the spectrum of the signal. However, because the continuous time Fourier transform, because of its namesake, is continuous in nature, it's not able to be evaluated numerically as yet, unless we do a few mathematical properties of it. Because in DSP we're dealing with discrete time signals, that means we need to figure out how we can move from the continuous time Fourier transform into the discrete time Fourier transform instead. And remember, these discrete time signals are basically a sequence of numbers being a one-dimensional vector. So the questions that we need to ask here is, how do we move from a continuous time signal x of t to the discrete representation of it known as x of n, if there are going to be any restrictions in doing this, and then how can we evaluate that CTFT on x of n if it's possible. So I'm going to be answering each one of these questions in turn in this lecture. So in doing sampling here, and we've seen some sample signals already in the last few lectures, basically what it does is just basically we set a sampling time, which tends to be constant, and we take the instantaneous value for each instance of the sampling time from our continuous time signal. And because this x-axis here with respect to n, this will represent the instance at which the sample was taken with respect to the sampling time. So this will mean at minus 20 here, then this will be minus 19, minus 18, and so forth and whatnot, representing the sample number of respect to the number of samples that we actually take. Now, one thing we need to discuss here is what happens when we start varying the sampling time in general. So, in this case, where we have our example graph here showing the stock price that varies per week, you can see here that the samples here that when we take them, it's a nice accurate representation of our continuous time graph here, because the sampling time here is adequate enough to represent these changes. However, this is like a nice example of an actual stock exchange graph where the sampling period here is 5 minutes and the x-axis here being 1, 2, 3 represents each instance of 5 minutes where we have these changes and so forth. But however, let's say the sampling time is varied and it's not regular or it's too wide in nature. It's possible for you to actually miss changes in the graph entirely, as we can see here in between T3 and T4. So if we took a sample here at T3 and then we increased the sampling time and we said, okay, we're going to take it at T4 here, we missed this entire dip in the change of graph entirely. So when you try to reapproximate back to the continuous time equivalent, it comes like we don't even see this dip entirely. We just see this dotted line here being, okay, there was no change whatsoever, or everything seemed to be normal. And in this one here, this is where T1 and T2, yes, the sample time is constant, but it's very large in nature. So we still miss this dip entirely. So this brings us to an important point of what's the trade-off of having a small sampling time and a large sampling time. A small sampling time means that you take more samples, but it also means that you require more memory to house these samples. In turn, excuse me, right, in turn, that means that if you have more samples, you have a higher accuracy representation of your continuous time signal. On the other side, if you have a larger sampling time, that means you take less samples and you require less memory to store these samples. But however, that also means that you're going to have a less accuracy representation of your continuous time signal when you start to reconstruct your signal. So when it comes to dealing with actual real-world DSPs and so forth, you're going to have to make a trade-off as to what's your memory requirements and what's going to be your accuracy requirements to adjust what your required sampler time is going to be when you're sampling any continuous time signal to get this discrete time signal representation. And sampling time, basically, if you take 1 divided by this, you'll get the sampling frequency. So the terms sampling time and sampling frequency are often interchanged once you're reading it in some text or any material regarding DSP whatsoever. So we have already seen how we can actually obtain samples of the signal. And this was basically when we had our convolution sum here in particular, where this delta n minus k here represents our impulse train that was basically being shifted for each sample here entirely. So, and using this convolution sum that we formulated a few lectures back, and using delta n minus k, which represents our shifted impulse, remember when we multiplied that shifted impulse by our x of k sample, we were able to extract out each sample individually, as you can see here in the figure above. So if you wanted our -2 sample here, this will just mean x of -2 multiplied by delta of n plus 2. And remember, the magnitude of delta for any one of these shifts being n plus 2, n plus 1, n, and so forth, or just a magnitude of 1 here. So this comes like we're just sampling at the -2 index, and we multiply by a magnitude of 1 here to obtain the true value of x minus 2. Same thing for x minus 1, 0, 1, and 2 here in particular. So in general, from using that convolution sum, that means that for any continuous time signal, if we multiply it by any impulse train, that means we just basically obtain a series of weighted impulse that are going to be spaced by t for each 2 successive impulses. And the mathematical notation for that is going to be delta of t minus n capital T as of such. What this also means is that in multiplying the continuous time signal here by this discrete time series of impulses, we effectively sample the signal So that way we get our discrete time representation of the continuous time signal. And as such, y of nt here represents our discrete time representation of x of nt when it's multiplied by our series of weighted impulses here, s of nt. So this comes like if we take a generic sinusoid wave here, and then we multiply it by our impulse stream, but remember the samples in between the impulses here are just going to be 0. So effectively we just sample out at each sample here, which is going to be spaced t seconds apart, and we obtain our samples here accordingly for each one of these sample periods as of such to obtain our discrete time representation of this continuous time sinusoid. Now the question is, if we need to move this into the frequency domain, we're going to have to figure out what's going to be, how do we apply the continuous time Fourier transform here in general to our weighted impulse series that we just saw. Because it's possible to apply the continuous time Fourier transform to any continuous time signal, but are going to be the restrictions in applying it to a discrete time signal instead. That's what we're going to be investigating now. So we know that the continuous time Fourier transform is given by this x of omega equation here. And if we do this accordingly to s of nt here, we're going to get s of omega here, where it's going to be 1 on t summation series between positive infinity and negative infinity of delta omega minus n omega s, where omega s is basically representing the sampling frequency in particular, which is also respect to the sampling time. So what happens is when we Fourier transform the continuous time Fourier transform of our s of t signal here, so get it in respect to s of nt here, when we transform it and we get s of omega, all that changes really is the values on the x-axis here. So instead of it being at 0t, 2t, 3t and whatnot, and now it's going to be at 0 and 2 pi on t, and then 4 pi on t, and 6 pi on t, and respectively on the negative axis, minus 2 pi, minus 4 pi, all divided by t and 1. So each instance of t here is just basically going to be repeated at every 2 pi cycles. And because this is frequency, that means you're going to be dividing by t, because frequency is equal to 1 divided by t accordingly. So in general, you just basically get a series of impulses that's going to be spaced 1 on t or f of s, where f of s is our sampling frequency, and that's the space in between two successive impulses in its Fourier domain representation or the frequency domain representation. Now, also remember that one of the properties of convolution was that if you have a multiplication in the time domain, that means it's just a convolution in the frequency domain, as well as if you had a multiplication in the frequency domain, that's a convolution in the time domain. So if we do some mathematical representations here and we substitute our s of f from the previous slide here to be the 1 on t equation that we just now had, and instead of it being t, it's now going to be f and minus n f of s and so forth. We're going to have to analyze what's the implication of this when we actually do start applying it to convolution in the frequency domain. So the only way convolution can be observed is that if the modulation property is observed as well, such that if we have a multiplication of x of t and y of t, that's going to be similar to if we had 1 and 2 pi and then the convolution of x of omega with y of omega here. And that convolution in general, that means we have to transfer this 1 and 2 pi to be integrated between positive infinity and negative infinity of x of k and y of n minus k with respect to dn, because now this is an n signal here in particular. So what that means is that if we convolve our x of f signal here being the frequency domain representation of x of t, with our s of s signal here being the frequency domain representation of that impulse, we get that such that The y of s signal is just going to be this x of s signal superimposed and centralized about the impulse here in the frequency domain. So this x of s signal here, instead of being centralized around 0, is not going to be centralized around f0 here in particular. Where we had b and minus b, that's just going to be f0 plus b and f0 minus b. So this is going to be the general result of the frequency domain convolution that we just saw in the previous slide. So if we have repeated instances of this delta f minus f0, so like f minus 2f0, f minus 3f0, or f plus f0, and so forth, that means for every impulse here that we convolve with, the signal spectrum here is going to be repeated at every instance of those impulses in particular. So in general, once we convolve this frequency domain representation here of x of t with the impulse train s of j omega here, which was basically s of n and its equivalent frequency domain representation, every impulse here in the frequency domain, we're just going to be repeating our x of f signal here for every impulse, and it's just going to be centralized around every impulse as of such. In this particular case, delta s here being omega s here representing each instance of our sampling frequency, given by this equation here, which is 2 pi divided by our sampling time. And this also gives us our sampling frequency equation in particular. This process here, when we do this convolution of our x of f signal with the s of f impulse train, this is what we refer to as spectrum replication. If delta of s changes here, we're going to get a different effect where the spacing between each one of these replicated spectrums is going to be increased, or it starts decreasing in particular. And we want to see what happens when it starts decreasing. So when our omega of s value here starts to decrease, spectrum replications themselves tend to get closer and closer together. And eventually they start overlapping with each other. So the relationship between omega s here and b is such that omega s plus b gives us our upper sideband frequency representation, whereas omega s minus b gives us our lower sideband representation here for our spectrums. So eventually, because they start getting closer and closer together, each one of these spectrums here will start overlapping. And then in the next few slides, we're going to observe what happens when we have this overlap in particular. So let's observe the spectrum of a general sinusoid wave sine of omega naught t. So if we Fourier transform this in particular, we'll get positive omega naught and minus omega naught in particular. But if we try to observe the spectrum of that same waves and we just increase the sampling period here, you may think, okay, it's going to be in between 4 omega naught here and minus 4 omega naught. But no, the spectrum actually remains the same because this is respect to sine omega naught t, and it only repeats for one instance of its periodic time. And in this case, it's just one instance of its periodic frequency. However, let's say if the sampling frequency here was not an integer multiple of the original sampling frequency here, which is basically 1 omega naught. So in this case, if we sampled at 1.5 omega naught instead, we're going to see that when we get our frequency domain representations, they're not going to line up with omega naught and minus omega naught. It's going to be in between and add some odd values in particular. And as of such, the replicated spectrum isn't going to be matching with omega naught and minus omega naught. So this effect here that what we get is that we get some frequency components that's not going to be part of the original signal and disappears in the spectrum because of this irregular sampling frequency. And this effect here is what we refer to as the aliasing effect. So this leads to the sampling theorem to make sure that you always sample your signals properly. And it's referred to as the Shannon sampling theorem or the Nyquist sampling theorem. And basically it just means that for any continuous time signal which you're going to sample, you want to make sure that you're always 2 times that of the sampling frequency and for proper sampling. Otherwise, you're going to get incorrect sampling, which is going to lead to the aliasing effect. So let's watch the cases here, in particular for each one of these 3 cases. So in this particular case, for case 1, the sampling frequency is much greater than the original signal frequency here. So we get our nice spectrum replication here, which we see here centralized around f of s and then 2 f of s. And we have our upper and side bands here represented accurately. When we're equal to twice that of the signal frequency here, with respect to the sampling frequency, we basically get the spectrums being very near to one another, but with no overlap whatsoever. However, when we have the sampling frequency here being less than twice that of the signal frequency, we then start to observe the aliasing effect, where these unwanted frequency components lie in between the upper sideband and the lower sideband representations of the frequency. And if we try to replicate this, we're going to get different sampling points here entirely that don't line up with the sampling period of the original signal in particular. So as a result, when we start doing that, that means we start getting spectrum overlaps from our spectrum replication process. And even if we bandpass filter this, represented by BPF here, we end up truncating parts of our original spectrum to begin with, for each instance of our f of 0, 2 f of 0, and 3 f of 0. So in doing so, that means when we do our bandpass filter and we bandlimit the signal less than twice the sampling frequency, we basically truncate our spectrum accordingly, so we can't get back an accurate replication of our original continuous time signal, because we basically we're missing some frequency data altogether. So ideal sampling is when we had that nice mathematical notation of the impulse, but we know in the real world an impulse doesn't exist. What happens here is that we use some really small rectangular windows, but as small as possible, with the time width being common theta here. I can't remember the Greek letter right now, but this common t symbol here. And we try to make this common t symbol very small as possible in order to replicate it close to our original sampling signal. So that rectangular pulse is given by this equation here, such that the magnitude here is going to be 1 in between that time interval and 0 elsewhere. And the space in between each one of these rectangular pulses here is going to represent our sampling time in general. So if we try to take the Fourier transform of this pulse, and we do the mathematics fit and so on, we're going to realize that the Fourier transform of any pulse is just basically going to give us a sync signal here. So it's going to be the frequency domain representation of our rectangular time signal that we just had. If we take the Fourier transform of a pulse train, we still get the same sync spectrum, but now we get some individual sidebands here in particular. And the amplitude here is basically going to be scaled by that sync function in particular. We also observed this earlier in our Fourier series recap that we did in our previous lectures. So each one of these amplitudes here are going to be scaled because of that sync function being a function of theta and f. F here is going to be respect to 1 on t, and each 0 crossing here is going to be respect to theta here in particular. So each 0 here is going to be at n divided by theta because of the sign pi theta f, or 0, and the impulses here are going to be at n divided by t as of such for the scaling of the amplitude. So whenever we refer to the envelope of a signal, it's basically we're saying the same thing as the frequency domain representation of that signal as of such. So if we take the envelope of the impulse train, that comes like if we take the Fourier domain representation of the impulse train, giving us our sync function exactly. And in sampling this in particular, we have some magnitude scaling on the original frequency spectrum, which we're observing here in particular. So as of such, whereas the original spectrum here is given by this red dotted line, but it's given by this nice spectrum replication of our triangles there. When we actually apply the sync envelope, we also get some truncation here as well for our sidebands. The original part here, because this is going to be a magnitude of 1, we get back a nice representation at this centralized frequency. But for each sideband, get some truncation here, resulting in these sidebands here in particular having amplitude scaling as well, but instead of the central frequency band here in particular. Each one of these truncated bands here is what we're going to refer to as images in the frequency domain. So as the width of each one of these rectangular pulses here increase, we get closer and closer to an actual large rectangular pulse. And once we convolve that, we're not going to get a nice accurate representation as required. Because now our time here for each one of these rectangular pulses has increased, so we get lower accuracy in general. So as of such, that means once we start doing that, we truncate more and more for each one of the sidebands, increasing the time of the rectangular pulse in particular. As of such, what happens is that the zeros of the sinc function and the period of the impulses end up coincided, such that 1 on tau here is now going to be equal to 1 on t. We will still maintain the central frequency here being the spectrum of the sample signals, but each one of those sidebands that we observed here is going to be truncated heavily as a result. So if we're given a simple signal here, we need to reconstruct the original continuous time signal. We need to look at the spectrum of the sample signal to start doing this reconstruction. So if we have a nice spectral replication here for our centralized frequency, and in some cases for our sideband frequencies, it's easy enough for us to actually replicate back to our original continuous time signal. If you pass this spectrum replication signal here through an ideal low-pass filter, we just focus only on the centralized frequency and we eliminate all the sideband frequencies as of such. And because we only deal with one part of our spectrum, being the original part of our spectrum here, and we eliminate all the replications, it's possible for us just to reconstruct the continuous time signal by using this Fourier transform. So the question is, what's going to be the impulse response of our ideal low-pass filter? And that also gives us a sinc wave representation. And the reason for this being is that this impulse response of the ideal low-pass filter, when you do the mathematics behind it, and you realize that goes to the sinc function, because this ideal low-pass filter has an infinite time response and it's anti-causal. And the ideal low-pass filter doesn't exist, so this isn't realizable in general practice. So in order to get around this, you can use an approximation of the actual low-pass filter to get as close as possible, or you can actually do signal reconstruction using this general algorithm here, which is basically you start with the data sequence and use something we refer to as a sample and hold circuit, which basically simulates those rectangular pulses with that really small time window tau. And as a result, when you do that, you basically get a staircase approximation of the original signal, which is and this process is what we refer to as staircase interpolation, reconstructing this. And if we basically get the spectrum of the reconstructed signal, that means if we're checking the impulse train here and we're convolving it with a rectangular pulse here, and the impulse train period and pulse width here needs to be equal in particular. So we end up getting that centralized frequency here, getting our nice reconstructed, so when we frequency transform this, our Fourier transform is we'll get our centralized frequency here, giving us our bandwidth information, the centralized frequency. But each one of these sidebands here are also going to be truncated because of that instance where the width of the rectangular window is going to be equal to the sampling time in particular. So the implications of this is that once you start doing this and we observe such that the width of the rectangular pulse is going to be equal to that of the sampling time, the reconstructed signal is going to have entirely different frequency components from the original signal. And this is expected because of the staircase approximation that we just now did. So we just get like an approximate representation of our signal. And the smaller and smaller the rectangular window gets, in particular, we get a better accuracy representation or a better approximation to the original signal in particular. And all those sideband frequencies are basically going to be attenuated by the sync envelope, but whereas the centralized frequency there is going to be, we're going to maintain that information around the centralized frequency in particular. And those side lobe frequencies there are, or our side frequencies, as I just now mentioned. If we need to remove them, we need to use something referred to, we could either low pass filter them, but in general, we can also use a reconstruction system known as a zero order hole, which also uses low pass filtering to obtain only the information centralized around the centralized frequency. And just like sampling, the reconstruction process is also an approximation. So the low pass filter frequency response is compensated for the sync attenuation in this process, such that instead of getting this nice clear curve here in particular, once we apply the low pass filter and we convolute it, instead of this curve going upwards, this curve now goes downwards, resulting in those amplitude attenuations that we just now saw. Alright, that brings us to the end of our sampling lecture. Are there any particular questions that need to be addressed at this point? So yeah, when basically you see that a signal has been sampled at a certain frequency, so in your example 125 Hz, that means it's basically 125 sample points per second. Yeah, that's basically what it means. So every second you have 125 samples. The capital omega basically represents our frequency in particular. So that capital omega s that we saw was 2 pi divided by t. That's basically the same as if we were just saying f of s. However, the reason why we use f of s and then capital omega s is that f of s represents continuous frequency, whereas capital omega s represents discretized frequency. So that's the only key difference between the two. Yeah, the term sample time and sample frequency can be used interchangeably because remember, sampling time is just equal to 1 divided by the sampling frequency. So you'll, like, if you're checking additional text or any general information, the terms are used interchangeably because it's just of that representation. The time is basically equal to 1 divided by the frequency. Alright, doesn't look like we have any more questions, so we'll move on to our second lecture for today. So in this second lecture, we're going to show how we move from using all those sampling theory that we just now saw. We're going to move the continuous time Fourier transform into its discrete time Fourier transform representation. So we basically saw here that the Fourier series and the continuous time Fourier transform only operate on continuous time signals in the time domain. But however, our DSP course here, because we're using discrete time signals, that means we're going to have to formulate our own discrete time Fourier transform in order to get our frequency domain representations of these signals. We just now saw also that the continuous signals here are converted into discrete signals by the sampling process that we just now watched. And in order to do this, we basically did the multiplication of the continuous signal by an impulse train in order to get these samples and to formulate the discrete time signal representation of that continuous time signal. And the equation that was given to us to do this was given by the summation series here of x of t multiplied by delta of t minus n capital T of s in particular. So if we wish to take the Fourier transform of this sample signal and we observe the continuous time Fourier transform equation here, the first thing that we're going to note that if we try to put in our convolution equation that we just saw here, x of st, into this Fourier transform equation, and we try to actually evaluate this, and if we also assume linear time invariant systems such that we can break apart our integrations as of such, that means we can move that summation series that we just now had here and the inside of the integration to the outside of the integration. And then we can try to just to evaluate just its integral part alone. And evaluating the integral parts alone, remember that this integration here, being x of t, being delta of t minus n t of s here, is basically the shifting property that we observed a few lectures back. And as of such, because it's the shifting property, that means we can rewrite this entire integration part here to x of n t of s instead, multiplied by our e j omega t here. But t here now is going to be n t of s with respect to our discrete time representation. So note that in doing the application of the shifting property here and making sure that everything lines up with our discrete time sampling, instead of having t here, we're now going to be analyzing everything here with respect to n t of s, where t of s represents our sampling time. But however, this omega here on the left hand side is still continuous in nature. We haven't transformed the entire equation into a discrete time representation just as yet. So If that x n t of s is replaced with x of n, and we say that omega t of s is equal to capital omega, being our discretized frequency, it becomes possible for us to transform that equation even further into our discrete time Fourier transform representation. And this equation here, represented in the green shaded block, represents our discrete time Fourier transform, or DTFT, of our general discrete time representation of the signal x of n, where capital omega here is digital frequency as measured in radians. So we also need to analyze a few properties of the DTFT as well. We saw that basically in the last lecture, it's possible once you have a periodic spectrum, you're able to get a spectrum replication where the spectrum is continuous. So let's actually analyze the periodicity of that discrete time Fourier transform in particular. And we can remember all the way back in our signals and systems recap, a discrete time signal to be periodic, it needs to be such that x of n here is equal to x of common n plus capital N. And the DTFT spectrum was periodic with a period of 2 pi radians. And in order to prove this, if we let capital N here equals to 2 pi, we can see here that after we do our mathematical notation, we get back the same x of capital omega here, or x of capital omega plus 2 pi. And the reason for this is that a discrete time signal is only periodic with respect to 2 pi. And mathematically, that also means that the complex exponent here, being e of minus j 2 pi n, if we analyze this accordingly and we transform it back into its cosine and sine representations, this entire equation here will just resolve to 1 for any value of n. So the implication of this is that any spectrum produced by the DTFT is just going to be periodic, and it's going to repeat itself every 2 pi cycles. So the question that we need to ask is how this is going to be applied to spectrum replication that we just saw observed in our sampling lecture. So capital omega here is equal to common omega multiplied by t of s, where t of s is between our sampling time or sampling period. And in doing so, the DTFT maps that real frequency or continuous frequency omega, being common omega here, to the digital frequency capital omega with a period of 2 pi in particular. And we just observed that effect on the previous slide. In order to make sure that we do get our nice spectrum replication, we need to make sure that we observe the Nyquist rate in particular. So we need to be sampling at least twice that of the original signal frequency or greater than that. So mathematically, if we say the highest frequency in our signal being omega h, we need to determine omega s here, map it to omega h, where capital omega is equal to pi, and we do some mathematical notation here, we basically see that we can prove that omega s here, being our sampling frequency, needs to be equal to twice that or greater than twice that of the highest original signal frequency in particular. So this basically gives us the proof for the Nyquist rate in order to satisfy the discrete time Fourier transform. So let's actually start observing some effects of the continuous time Fourier transform and the discrete time Fourier transform and compare the two. So we have our continuous time Fourier transform here on our rectangular signal, and we apply it here to our problem. We basically see that we'll get our nice sinc equation here in particular, and if we MATLAB implement this, we basically get our nice sinc wave. But remember, this being here the continuous time Fourier transform, that means the spectrum here is going to be continuous in nature. So if we plot that magnitude of the spectrum, we get our nice sinc wave here with our nice side bands and so forth and what. Now let's actually observe what happens when we actually sample the signal and then we apply this to the DTFT instead, where our sample time here is going to be 0.2 seconds. So applying this into our problem here, and we're going to be applying it to the DTFT equation here. we resolve our summation series here to 2 and -2, because that's the limits of our sampling. And the magnitude here is just going to be 1, so our x of n here is just going to be 1 for every value of n. And we just have the e of minus g n capital omega to evaluate. Now, we know capital omega here is equal to common omega t of s, where t of s is our sampling period. So we can substitute that in normally into our exponents and evaluate the summation series. But in evaluating the summation series, we basically see once we transform these exponents here back into its cosine and sine terms, the sine terms here are minus j, which means they are minus imaginary parts. So as a result of having a positive 0.4 pi f here and then negative 0.4 pi f here, all the imaginary parts cancel each other and all the cosine parts just become 2 of the original cosines, because they just add together all together. So the x of capital omega here is going to be 1 plus 2 cosine of 0.4 and then 0.8 pi f in particular. If we plot the magnitude of the spectrum using the DTFT, we see here, because we get spectrum replication, we have multiple instances where the spectrum keeps on repeating itself. And if we analyze just only the centralized parts of these spectrums, you can see here that CTFT being the actual true plot and the 5-sample DTFT, we basically see that the DTFT here is an approximation to the CTFT. And if we keep on increasing the number of samples, we get closer and closer to the actual real frequency domain representation in continuous time. So let's actually observe this effect if we take more samples and we just lower our sampling time in particular. And we actually do the discrete time Fourier transform of this. We see here that we get a more accurate representation of the continuous time Fourier transform with respect to our discrete time Fourier transform here. And in comparing it, we see here that the 9-sample DTFT gets very closer to our actual CTFT representation of the signal. So the more samples you have, you get a more accurate frequency representation. The less samples you have, it's less accurate. But remember, the trade-off is that more samples means more memory, less samples means less memory. And so if we compare the two DTFTs here, this here on the left being the 5-sample DTFT and the 9-sample DTFT, you can see how it starts approaching more and more towards the actual continuous time frequency representation of that signal. So in comparing the resolution, you'll get continuous spectra, yes, and we still resolve the same frequency components. The only difference is that we have some amplitude scaling because of the number of samples in particular. And this is just an effect of using the DTFT, so you won't have to rescale your amplitudes accordingly back to the CTFT by some amplitude factor, which it just tends to be a division that you do for the entire graph. And as you increase the number of samples, you get closer and closer to the actual CTFT representation, so you get a higher accuracy representation. The aliasing effect will be noticed such that if the pulse at high frequency components, that won't be sampled at their Nyquist rate. And aliasing accounts for some of the amplitude differences that we just now saw between each spectra in particular. So as with the DTFT, inverse DTFT also exists, and it's given by this equation. And that allows us to move back from the discrete time frequency representation of the signal into the discrete time representation of the signal itself. This slide here basically shows us the comparison between the CTFT and the DTFT, where we see all the integrals here just become summations, x of t becomes x of n, anything that was common t here becomes n of capital omega. Same thing for the inverse, we can see the same properties being applied, but however the inverse here uses an integral instead of summation, in particular to get back to x of n. And we also see here that if we use the complex exponential form here, this is still respect to time, and this here is respect to frequency. And we also see here there's the ck of k here is respect to frequency here. X of n here is with respect to samples and time in particular. So basically, if we take any of the Fourier series equations and we make these following substitutions here, it's possible to obtain the DTFT pair immediately by just putting in these substitutions. Alright, that brings us to the end of our DTFT lecture in particular. And even though we start observing how we move from the CTFT to the DTFT, this isn't the actual frequency domain transform that we want to use for discrete time signals. This is just the start of how we actually start approaching to the actual frequency domain transform that which we require. So when we start observing next week's material in particular, we move to what we refer to as the DFT, which is the discrete Fourier transform, and then we move to the FFT, which is what we're going to be actually using. You see that each one of these are just going to be an approximation of each one of the other, and we just try to keep on mitigating the approximation effect as we keep on going along with respect to each one of these transforms. So are there any particular questions on the material delivered for the DTFT today? We try to avoid the aliasing effect because, as we saw in our sampling lecture, as we sample less than twice that of the original signal frequency, the spectrums start to overlap. And because they overlap, that means your frequency content in the overlap gets muddled or it gets interfered with. And if you try to remove these overlaps, you end up truncating part of your frequency information. And as of such, when you reconstruct the signal, you don't get back your nice accurate representation in the time domain. So we try our best to avoid the aliasing effect by always sampling twice that of the highest signal frequency in particular that exists in your continuous time signal to begin with. So that way, when you reconstruct the signal back into time from frequency, you get back an accurate reconstruction of the signal itself. Now, there are some cases where you cannot avoid aliasing, and in future lectures I'm going to show where you can't avoid the aliasing and how you can actually use some mitigation techniques to reduce the aliasing effect in particular. All right, any further questions? Yeah, I'm getting to that in a little bit. So, alright, so it looks like we don't have any further questions regarding the material of the lecture. Well, I know that I uploaded problem set 1 last week, and typically we'll end up doing problem set 1 today. But I actually have a couple of things that I need to take care of today that it's quite urgent and I can't avoid. So instead, we will be doing problem set 1 next week, Wednesday, after we conclude our lecture sessions. In particular, I'll put up a choice of I'll put up a choice on My Learning, where we choose like the top 3 questions that gave you the most problems, sorry. And we'll do those 3 questions in particular live in Wednesday's session next week. And if we still have any additional time after we do those 3 questions, any other questions from the problem set, we can also tackle and so forth. But I'll also post up the solutions for problem set 1 after that session next week in particular, any review. So from this week till next week, do attempt the questions on problem set 1. And like I said, I'll put up a choice on My Learning for you guys to select which 3 questions gave you the most trouble. And after that choice closes off, I'll watch the results of that poll and figure out, okay, which 3 questions we're going to be doing. If there are any other questions after we do those questions in particular next week, and we still have time, we'll also do those questions as well. Now, the last question in problem set 1 is a practice question for you guys to do on your own. And that actually is going to give you a little more real-world DSP experience as to actually applying DSP techniques into your actual signals. So it's highly suggested that you actually do attempt this in particular. And this isn't more of a question, this is more like of a walkthrough in particular to give you an idea of how to actually apply DSP techniques to real-world signals and using MATLAB, Octave, or whatever platform you wish to use that's somewhat like a MATLAB equivalent. But the instruction set is basically written for MATLAB in particular, so it's kind of advantageous if you do end up getting MATLAB. I think Octave can also do it as well, just some of the commands just have different names in particular. But it's up to you which one you want to use for actually applying these techniques. Right, so next week, what we're going to be doing, the discrete Fourier transform known as the DFT, and then we will move on to the fast Fourier transform, which is basically what we're going to be using for any frequency domain representation of our signals throughout the entire course. And that is the technique that we're going to be using throughout the entire course, the fast Fourier transform, and how it can actually be applied to our numerical representations of our discrete time signals in particular. We also introduced the technique used to actually perform the fast Fourier transform manually, as well as how do we evaluate the fast Fourier transform from our discrete time sequence of numbers, and so forth. Also, after the lecture sessions on Wednesday, we'll be doing problem set 1 afterwards, and like I said, the 3 questions that gave you guys the most trouble, we'll be doing those in order first, and once we have any additional time, we'll do any additional questions that are required. Just make sure that you do the last question on problem set 1, because like I said, that's not really a question, that's more like of a walkthrough to actually you guys to get some real world experience to apply DSP techniques onto real world signals. So if there are any further questions regarding the materials of this lecture, feel free to leave them down in the comments below, or you can directly email me and I'll respond to you guys. But until next week, take care, be safe, and I will see you guys soon. Later.